Okay, this section is called Deciphering Neural Networks. And what it talks about is how to use neural network to create a specific function. Remember, a neural network takes inputs and produces an output. So in this case, we'll see how the power of neural networks works. When you stack layers, you can create functions which you could not otherwise. The particular function we're going to look at is called the XOR function, and this is important for historical reasons, because the earliest neural networks were called single-layer perceptron and only had one layer, and it was mathematically discovered that they cannot model an XOR function. It take at least one hidden layer to model an XOR function, and we'll see explicitly how to create that network with one hidden layer. All right, so let's begin. All right, so what is the XOR function? We have two variables, so it's a function of two variables, and XOR means one or the other, but not both. So the 0 and 1 you can think of as yes or no. So 1 is yes, 0 is no. Okay. So XOR means that exactly 1 is yes. If they're both no, the output is no. If they're both yes, the output is no. So you can see the output here. Now if we plot the two variables in a continuous plane, because often these variables are not just sharp values, but more fuzzy values, you can see that 0, 0 is here. So this is a definite, so x1 and x2, that's a definite XOR value of 0. Here's a definite XOR value of 1. Here's a definite XOR value of 1 also. And then this is a definite XOR value of 0. All right, so you can see how this function works. But what about in the middle? Well, in the middle it's kind of mixed up. This is actually not the best way to represent it. In fact, what you should do is you should represent, if you let blue be no and red be yes, you should have a blue square here, you should have a blue square here, and you should have a red square here and a red square there. So you should have a 1 by 1 square divided into 4 subsquares. There's a kind of symmetry. So it's kind of like this. You should divide this into 4 squares. Blue square here, red square here, red square here, blue square here. And those are the regions that should correspond to the different values of XOR. So we want a function that's actually, and this is reversed here. This should be y equals 0, y equals 1. Right? So it should be 0 on this square, 0 on this square. So it's a funny looking function. It's got these discontinuous regions, which is difficult to model. Okay. So let's see. So the point here is that the XOR function does not divide the plane into simple regions. You can't just get a rectangle that characterizes one class. Okay, so it's not going to be simple. So we want to create a classifier for the XOR function. So here's another way of saying it. We can break it down into logical operations. If you've studied logic, these are logic gates. These are basic logic gates. X is 1 and x2 is not 1. Or x1 is not 1 and x2 is 1. It has to be one or the other. And you can see these are exclusive. It's not possible to have both of these cases at once. And it's possible to have neither of these cases. You could have x1 is not 1 and x2 is not 1, and that wouldn't be either class. Or you could have x1 is 1 and x2 is 1. That's not in either class. Okay. So we can break this down into fundamental logical operations. This AND operation operates first on x1 and x2. And this AND operation also operates on x1 and x2. And then we operate the OR on the two results. So this actually suggests a two-stage process. And those two stages are going to correspond to the two layers in our neural network. So that's what we're going to do. We're going to create a neuron that gives me this output, and another neuron that gives me this output. and then we'll connect those to a third neuron that combines the two. All right, so how do I get a neuron that gives me x1 and not x2? So we have inputs of x1 and x2. So this is a standard neuron. It has the constant input as well, which I call the bias. And here's the first output. And then you're going to take a nonlinear function of that. Right. So what do we want our output to be? Well, because this is AND, it's only going to be 1 or true if both conditions hold. So we need x1 to be equal to 1, and not x2 means that x2 is 0. So the only non-zero output should be when x1 is 1 and x2 is 0. So that's what our output should be. That's what we want the result of our nonlinear function on A2 to be. So how are we going to set the weights? Now you remember in our discussion of logistic regression, if we use a logistic function for our nonlinear function, then the output is going to be positive, or I'm going to make a decision of 1 if the input to the logistic function is greater than 0. And my output's going to be 0, my decision is going to be 0 if the input to the logistic function is negative. And the input to the logistic function is a linear combination of the inputs that were put into the network. So it's going to be theta 0 plus theta 1 x1 plus theta 2 x2. So what about our theta 0, theta 1, and theta 2? Well, let's try these weights here and see what our output's going to be. Well, if you have 0 and 0, what am I going to get? Well, then you get 1 times minus 10 plus 0 times 20 times plus 0 times minus 20. So that's what we got here, minus 10 plus 20 plus 20, but these two are 0. All right, so we can use this formula and just plug in x1 and x2 accordingly, right? So you'll get you'll get g of minus 10. Now remember, g is the logistic function. If g of minus 10 is very, very small, that's why these weights are big. It's going to make this very, very small. I could just make this minus 1, 2, and minus 2, but then the g of minus 1 is not so close to 0. But with these big weights, then g of this output is going to be very, very close to 0. Right? How about 0 and 1? Well, you can work out the formula again. It's going to be even smaller. In this case also, it's going to be even smaller. No, sorry. How about this case? In this case, what do we have? Well, in this case, there's no output from x2. So only this term is 0, and I have minus 10 plus 20. This is positive. Okay. All right, so I have a neural network that gives me the output I need on these inputs. So it's reproducing the output on given inputs. All right? So that's my AND function for x1 and not x2. Now you can imagine x2 and not x1 is the same way. You just reverse the roles of the two. Right? Before it was 1, 20, and minus 20. Now it's going to be 1, minus 20, and 20. You can see how that works. All right, so I can skip through this. You can see that it's working the same way. It's very symmetric. So you can look at this, you can pause the video and convince yourself that this all works here. You're just exchanging the roles of x1 and x2. Right? Now on the other hand, suppose we want an OR function with two inputs. Now this x1 and x2 are not going to be my original inputs. They're actually going to be the outputs from the two previous neurons. So let's go through the same process. We want an OR output. So here's our table. What does OR mean? OR means that one or the other, or both, should give me a 1. So that means that the only 0 should be when x1 and x2 are both 0. Right? So I should have here 0, 1, 1, 1. Okay. So how are we going to make these weights like this? Well, you can think about it this way. We want either x1 or x2 to trigger, and then we want 1 to inhibit. Okay? So 1 should have a negative weight, and x1 and x2 should have positive weights. So if you fiddle around a little bit, you'll find out that this works. And you create your function, and you find the values, right? If x2 and x1 are both 0, then the minus 10 takes over, and I get a 0 output. But if either x1 or x2 is 1, it overwhelms the weight from 1 and gives me a 1 output. Right. Again, this is g of minus 10, which is close to 0. This is going to be g of 10, which is very close to 1. This is g of 30, which is very close to 1. All right? So we've got our neural net. We've got several neurons here. One for our first condition, H1, one for our second condition, H2, and one for the OR, which is this here. All right. So this is H1, this is H2, and then this is H3. That's how we put them together. And you can see the colors show you how these 3 neurons are fitting into this structure. Right? So you can work this out, that you can get the values of H1 and H2 and see what happens to get these 2 values. And then A3 is going to be a combination of H1 and H2. So I'll let you work this out as an exercise. Just follow these equations, fill in these values according to these equations. Remember, g of a large negative number is 0, g of a large positive number is 1. So we can work this out. It's actually going to give me what I need. If you remember, this is the XOR function.